Hello everybody, and welcome to today's 30-minute session titled Overcoming the Performance Costs of Streaming Transactions, brought to you by Redpanda. I'd like to introduce you to our presenter, Roko Kruze. Roko leads the customer success team at Redpanda Data, where he supports new and active users of the Redpanda streaming data platform. Prior to Redpanda, Roko was at Cockroach Labs and Cloudera, where he helped to build multi-region applications and large-scale distributed systems supporting global applications. With that,
thank you so much. Yeah, so I am joining you today to talk about streaming transactions, and so let's get right into it. Probably the first question you have as we dive into this presentation is, what is Redpanda? Besides being an amazingly cute mascot, it's a little bit more than that. So let's dive into exactly what Redpanda is. Redpanda, really at sort of the core of it, is a specialized distributed replicated transactional storage. It allows for append-only writes, sequential reads. It has persistent cursors as you're reading that data, and also provides primitives for consumer cooperation when reading this data. So, very similar to like a queuing system, an event streaming system, and kind of very similar to Kafka. So similar to Kafka that we're Kafka API compatible. So if you have anything out there today that you're using with Kafka, whether it might be something like Flink, maybe you've built an application around the Kafka API using the different clients that exist out there, Redpanda is fully compatible with that Kafka API. So it allows you to very easily transition your applications from Kafka to Redpanda with only just having to change the location of the service itself without having to do any code changes. Redpanda is also based on Raft. So, we use Raft for all of our consensus metadata within Redpanda itself. We also use it for the replication of the data within Redpanda. So any data that you're sending to Redpanda gets persisted using Raft across multiple nodes. So that way we can handle failures and other things from that perspective. We are also built on an interesting library called C*. So Redpanda is fully written in C++. There's some utilities around it written in Go, but the core application or core Redpanda is written in C++, making use of C*. C* is a very interesting async framework that allows for asynchronous I/O, somewhat similar to like I/O Uring and things from that perspective. And what this allows us to do is it also provides us a model for doing a thread per core architecture, which what that really means is that Redpanda treats an individual machine as if it was made up of multiple discrete systems, each one being an individual core. And this allows us to do things like not having to do locking across cores because there's no shared resources, and also minimizing context switching and allowing us to be mindful when accessing memory. So we're not doing any sort of high memory or high latency memory requests in the system. So this really allows us to get the best performance possible out of the machines that we're running on top of. So much so that just, we won't dive into too much of the performance side of things. We actually have a blog post in our on our website that you can go check out after this talk if you're interested, where we've done some benchmarking against Redpanda versus Kafka. For this particular example, where we're doing 500 megabytes per second across 3 nodes, you can see this is, you can see the overall latency for Redpanda, stays right around 2 milliseconds for end-to-end latency. And for Kafka, it's a bit higher, right around 14 milliseconds. And what the other thing is that's very interesting is the overall tell latency. So you can see that Kafka gets out to about 3 seconds on this particular workload, and Redpanda stays pretty consistent at about 120 milliseconds. So this is all using the Open Message Benchmark framework, which is a Linux Foundation project. And we have a whole blog post on our website that goes into how we actually executed this and how you can actually reproduce these results for yourself. But this is really a result of the using Raft and also using the C* framework. I wanted to set this as kind of the baseline, and then just talking a little bit about the other sort of key benefits for Redpanda, and then we'll get into the transactions portion of it, because it's key to understand the performance implications and what Redpanda can do before we jump into the transactions, just to give us that kind of baseline foundation in the system. We are also focused on being reliable. So I mentioned we're using Raft. We have a single consensus algorithm inside of the system, so we don't have multiple fault domains. There's only really just that one system. There's no external dependencies, so we don't depend upon an etcd or Zookeeper or any other system to do consensus for us. We are fully fault tolerant and highly available. You can have multiple copies, and we automatically recover when you lose a node inside of a cluster. Using Raft is a quorum-based system, and this actually provides better availability than Kafka's in-sync replicas, is what ISR stands for. And we actually have another blog post on our website that goes into that level of detail too as well, which I would highly recommend, which talks about the availability footprint of Redpanda. The other key thing to know about Redpanda is that we're safe by default. So this is slightly different than other streaming systems out there today, where a lot of the times they can hold data in memory before they persist it to disk. And for us, we actually make sure to persist the data onto disk before acknowledging back to the client. So this gives a overall better data durability and reliability within the system itself. We also do a number of things around chaos testing. So we actually have a full repo in our GitHub organization that you can go take a look at, which shows the different chaos testing that we do on a regular basis. This does things like take a follower out of the cluster and sees what impact that has on the particular leader and the availability of that particular partition. And we've also done things like having third-party audits. So we've had these third-party audits come in where we've very similar to kind of the chaos testing to make sure that we are providing correctness in specific regards. So with that out of the way, let's talk about transactions in Redpanda. So I'm making a lot of assumptions around, hopefully you understand Kafka or have some familiarity with Kafka. And a lot of the semantics inside of Redpanda are very similar to Kafka. We have topics, partitions, and things from that perspective. And the other feature sets within Kafka is also the ability to have transactions within the API itself. So this is currently in a development preview or dev preview as of the current version of Redpanda, which is version 21.11. And you can enable a few different key aspects of this within the configuration. And you can come to our website and we have more information on how to actually do this. But one of the key things is around idempotent producers, which we're not going to really talk about that today. But what idempotent producers means is really reducing the number of duplicates or trying to get rid of duplicates altogether from a producing standpoint when you're producing messages into Redpanda. And then the next thing, which we will dive into in a bit more detail today, is around enabling transactions. So you can enable transactions with just setting the setting inside of Redpanda, which will enable the transactions API interface, so you can actually execute transactions through this API, through the Kafka API against Redpanda itself. So how is Redpanda typically used? If you're familiar with Kafka, these are pretty familiar use cases or pretty familiar streaming use cases that you see quite often. This one is a representation of using Redpanda as sort of the centralized messaging system within a framework. So you might have a set of microservices within your environment. Maybe you have some change data capture going into it. Perhaps these microservices are pushing data into Redpanda that then are being consumed by other downstream services that are pushing them in or pushing that data into a database or updating state elsewhere. As you can imagine, this is actually pretty critical or in these types of situations, transactions can be critical because you want to reduce the amount of duplicate messages. You don't want to, update a bank account multiple times or, have duplicate orders. So, in that particular case, transactions are absolutely critical. The other way that Redpanda gets used quite often is for what you see as change data capture. So, updates happen within a database, data gets put into Redpanda or pushed into Redpanda versus a change data capture tool. This might be something like a Debezium Or, this could be a specific integration that, just pushes out directly to the Kafka API. So it allows Redpanda to make use of that. And then that data can be pushed to a downstream system, like OLAP for analytical purposes. So, this is clearly the ClickHouse logo, but you could push it to a number of different data warehouses, whether it's Snowflake, Databricks, or BigQuery, or any of those types of systems that you would use for your analytical purposes. So let's get into the meat of it around transactions. So really you want all or nothing semantics for different types of use cases when you're writing to multiple topics, you're doing things like consuming, transforming, and producing data back into the cluster, and also for exactly once delivery. So let's talk about exactly once. This is something that everyone wants to have exactly once. It takes a fair amount of work throughout the whole architecture to do it, but let's talk about it in the aspects of Redpanda itself and applications consuming data from Redpanda. So you can see my drawing here where I have an input topic. This input topic could be data coming in from an external system. It's being put into that topic, and then I have a application that is consuming from that topic. Let's say it then does some type of transformation to that data and pushes it to an output topic. What I want to make sure, though, is that as I consume from that input topic and push to the output topic, I do this in a all or nothing semantic, or inside of a transaction itself. And the way that we also track where we're at from an input topic standpoint is also writing to an offset topic. So this offset topic tells me, or tells the application, or tells all the applications that are consuming from this topic where we're at with the consumption of data from that input topic. So you can imagine the flow goes from I consume data from the input topic based upon the latest offset that says that data has been consumed up to this point. I do some type of transformation, I push it to the output topic, and then I update the offsets to say that that piece of data has been processed by this application. Now you can see where duplicates could come in this particular example, because let's say I'm not doing this within a transaction. So I read from an input topic and then I put it to an output topic, but then my application crashes. And then the application comes back up again, and it sees that it goes to the offsets to see what was the latest offset that was updated. Since the offset wasn't updated with the transaction, it's going to retry that particular message, or the last offset that the previous application saw. It will pull that, do its transformation, and then create a duplicate on the output topic. So really what you want is to actually do this all within a transaction. And more specifically, you want the transaction to be across the offset topic and the output topic. So then that way you either have the write completely succeed, or you have it fail, and then you roll back all of that data or abort the transaction for those particular examples. So this is really around helping with that exactly once semantic. As I mentioned earlier, idempotent producers also helps with this, but this is definitely one of those key things, or this is a key thing for that too as well. So let's talk about a more specific use case of this, or for transactions itself. So let's come up with, or here's kind of a fictional bank, if you will, where I have a number of accounts, and those accounts are specified to specific databases. And my database in this particular example is really acting as a snapshot, and Redpanda is acting as the ledger. So you can really, this is actually something that we see a number of users actually use this in, or in this regard, where the sort of write-ahead log or the ledger itself is inside of Redpanda, and then a snapshot is taken every so often to give the current balance, so that you can do balance lookups quickly, but you have a whole history of how you actually got to that balance within the ledger of Redpanda itself. So let's just come up with this idea of different services being built on top of this. So let's say each service has its own topic inside of Redpanda and has its own table within the database. And using that, we can talk about different things that we might want to do or do in this particular application. One might be is checking the balance. That's something as simple as going to a REST endpoint, talking to the database, and asking for the current balance from that snapshot, which that's pretty straightforward. We don't actually have to involve the ledger or Redpanda in that regard. But when we want to move money between users' accounts, this is where the ledger has to be. We do have to get the ledger involved. And this is also where transactions are critical, because if I'm moving data from one account and then putting it into another, I want to make sure that I'm doing that in an all or nothing fashion, and not just deducting money from one account and then never getting that put into another account down the line. So, we want to read the personalized ledger and update the balance, check that both the accounts have enough money before scheduling a transfer to another user, and then execute that cross-ledger transaction as I just mentioned. So in the most simplistic of terms, it looks something like a begin transaction. So I start my transaction, and then I'm sending sending to the ledger 2 different updates. I'm going to deduct a certain amount of money from account 1, and then I'm going to add that amount of money to account 2, and then I'm going to finalize that transaction. So let's take a look at what actually happens behind the scenes from a transactional standpoint. So what I'm going to show you first is what this looks like in a typical streaming platform, more specifically Kafka, where it's actually doing a 2-phase commit. And if you've worked with databases or you've done transactions in other systems, a 2-phase commit is something that is pretty well known. And then after that, we're going to talk a little bit more about how we've optimized this inside of Redpanda itself using parallel commits. So let's talk about like the more traditional way of how this is done, where the client will register with the coordinator. This is the transaction coordinator within the system that we want to interact with account 1, and we also want to interact with account 2. And we're assuming that those are 2 different topics. And at that point, the coordinator is going to mark across those topics that we have started a transaction, and that has to be persisted onto disk. And then we return back to the client that we are ready to start the transaction itself. So now let's talk about when we actually do the deduction and the addition to the other account. So we do our send command to update account 1. And then also we update account 2 to move the money from account 1 to account 2. Both of these have to be persisted onto into those topics. And you see 3 little hard drives because typically you're replicating this data 3 times. So we have to have the data be fully replicated across the cluster, or typically replicated across the majority of the replicas before we move forward. So we're updating both of those topics for account 1 and account 2, and then returning back to the client that that's been successful. And then lastly, we have to commit this transaction. So now we specify a commit to the coordinator. This has to go out and specify that now I am finally committing that transaction. I acknowledge back to the client that the transaction is in a committing state. And then I have to go back and update the different accounts to let them know that that has been fully committed and is the most recent up-to-date data. The other thing I should acknowledge or should mention is that within Kafka itself and also within Redpanda, with this type of approach to doing transactions, you are going to get a read committed transaction isolation level. It's not possible to do linearizable or serializable or other things from that standpoint. It's you are getting read committed. So at this point, this has been committed, and then now you can actually see that as sort of the current state of data within the system. So and then we tell the coordinator that that has been fully committed, and then we return. So as you can see, that was a number of times back and forth that we had to return back to the client, and a lot of times that we have to touch disk to actually get the transaction to be completed. So the optimizations that we've decided to take, or the approach that we've decided to take, is to actually allow that send command to be eventually consistent and validate that everything's fully replicated during the final commit phase, and also to do parallel commits versus previously you're seeing sort of more of a serial. We do we're committing to one account and then to the other account, and then also we're storing a lot of this data that would typically be persisted on the coordinator onto disk, actually storing this data in RAM. This is a very similar approach to what Cockroach Labs has taken with their parallel commits. It's really based on a lot of the flexible Paxos principles that have been sort of talked about and researched in the last couple of years. So with this approach, it looks slightly different. We start our transaction. So we talk to the coordinator about the two different topics that we want to talk about, account 1 and account 2. We check the term. So what is this? The term is that we are checking to see that what is the latest offset or ID within those topics, so that we can understand where sort of the state of those accounts is at. So this would be kind of a sequence ID, if you will. So we're checking, we're getting the latest of that information from the two different accounts that we're interacting with in this regard. We store that term data into the coordinator's memory, and then we return back to the client that we're ready for the transaction itself. Now we do the send portion of it, where now we're going to send the update to the two different accounts. This is going to be done in a parallel fashion. We don't have to wait for any acknowledgement. And we're only just really checking, or we're only just really persisting this on the leader. We're not having to fully replicate this just yet, because this is a temporary state of the actual transaction. This hasn't been fully committed yet. And we haven't told the client that it has been fully committed. So there's no need to fully replicate this data across the cluster. So this is the eventually consistent portion of this. In some ways, you could think of this as using AX equals 1, where we're just verifying that the leader has replicated this data, or the leader has written this data to disk, I should say. And then now the final step is the actual commit. So the commit, what's happening here is now the client is talking to the coordinator to say, I want to finally commit this transaction. I'm done with the updates. And then this prepares the transaction. This is when we actually fully start to write everything to disk on the coordinator side of things. And we're checking to make sure that that term has not changed. So what this means is that that term that we picked up in that first step, we verify that it hasn't increased during the period of the transaction itself. And if it has, we return back the standard error to the client to let them know that they need to redo their transaction because the state has changed under them behind the scenes. So, it's very similar to like a retriable error that you might see in a serializable type of system or a serializable isolation level. But this only really is an issue if you have conflicts or multiple overlapping transactions. And if you don't have overlapping transactions, this doesn't become an issue in that regard. So we check that the barrier term exists. We do the preparing and write that to disk. And then we ACK back to the client that this has been completed. And then this has been all done in a parallel commit fashion. So we're not having to, we're sort of, the coordinator is doing a parallel commit across the accounts because we're sure that the term is within the barrier that we've defined. And this allows us to more quickly do the actual commit and writing to disk. So as you could see from this example versus the previous example, there's a lot less disk interaction or replication that has to be waited on and throughout the whole process. And then we do the final prepared and the final sort of finalization of it from the coordinator standpoint. And this is the sort of last kind of step of updating where we are at from a memory standpoint, and then returning that, just kind of cleaning up the last steps of the transaction itself. So that's great. Like this is kind of a newer approach or a newer way to to handle these types of transactions within the stream platform. And the question might come is, what sort of benefit does this give me? So in the testing that we've done, This was, this was just doing the simple moving of transferring between two random partitions out of 64 partitions on a, standard 3-node cluster. Is that you can see that as we increase the total number of threads, the throughput on Redpanda stays pretty consistent. The average throughput stays right around the 5,000 transactions per second. And also you can see that our P50 latency in milliseconds below, it does increase as more threads are added. And this is to be expected because if we have 250 threads, and we're randomly picking out of 64 partitions, we're going to have times where there are overlaps or collisions in the transactions that are being executed. And so there's going to have to be retries. And as those retries occurs, that's going to increase the overall latency for the actual interaction. But what does this compare to a system like Kafka that's actually doing a two-phase commit? So you can see here, Kafka stays at about 1,000 transactions per second. That's sort of its limit because it's doing a lot more work behind the scenes. It's not doing the eventual consistency of the actual transaction itself. It's having to do a lot more, it's having to wait a lot more for disk. And then also we can see that as the number of threads increase, our latency increases much more dramatically or at a much higher slope. And this is all due to the fact that there are more steps involved, and there's also going to have to do things like retry those transactions as well if they have conflicting transactions. But since it's a little more of an involved process, the overall latency increases faster within the system. So with that, thank you so much for listening, kind of following through on transactions in the streaming platform. Hopefully this was helpful to give you kind of at least the initial glance at what transactions look like inside of Redpanda and how that works. Please do come and check out Redpanda itself. You can see all the code for Redpanda in our GitHub space, and there's the link for that. We also have a number of blog posts which I referenced. We have one around benchmarking Redpanda against Kafka, the availability footprint of Redpanda, and also the chaos, that covers a lot of the chaos testing that we've done. And there's a lot of great, very technical content on there for you to peruse. We also have a very active Slack community where feel free to come and join and ask any questions. If you want to dive deeper into some of the things that we've done around transactions, we have the engineers who have actually developed and put this together that we would be happy to talk to you about it more specifically. Or if you want to know more about Redpanda and what we potentially could help you with in regards to using Redpanda for your application or for your use case, do feel free to reach out to us and set up a one-on-one meeting where we could take you into more in-depth features of Redpanda and help you out with what an evaluation might look like for Redpanda itself. So with that, thank you so much for your time today. Really appreciate it, and I'll hand it back to you, Lucy.
All right, well, thank you. And DZone would like to thank Roko for a great presentation. DZone would also like to thank Redpanda for providing the audience with a great session. And lastly, thank you to everyone who tuned in today. We hope you learned something new that will help you in your developer career.